YouTube.
Ok, allora intanto faccio entrare tutti.
Sì, fai entrare tutti e ti faccio una breve presentazione io.
Okay.
Sorry, Prof. Can you upload the slide, please?
The presentation?
Yes.
Okay, I ask you to wait because Luca Vezzaro, Professor Luca Vezzaro, what you are seeing here, in one of the windows, will upload the slide this afternoon.
Yes, sorry, I forgot to send to.
Okay, thank you.
So, good morning. Thank you to everybody joining the class. Today, you will have a very interesting seminar held by Professor Luca Vezzaro, that is working in Denmark, was one of your colleagues because he graduated in Padua, and now he's working in Denmark at DTU. Sei al DTU, vero Luca?
Yes.
Okay. So the lecture of today is about evaluating uncertainties. And by now you should have clear that uncertainty is a key aspect of ecological model as it is in all mathematical modeling applications. So please follow the lecture. This lecture will be recorded, so you will find it also on the YouTube channel of the class. Okay, Luca, please, it is your turn now.
Thank you. From one Luca to the next Luca. I hope you are awake this morning, coming back from Christmas holiday. So, as Luca said, I'm Associate Professor at the Technical University of Denmark, and as Luca said, I come from Padua, actually from Volta Barozzo, the Center of Environmental Engineering. That's actually where I'm transmitting right now, since I escaped from the grayness of Denmark. But since 2007, I went to work at DTU, where I work with modeling water quality in sewer systems. So basically dirty water in sewers, very nasty stuff and very uncertain. And of course, I've been emitting a lot of CO2 going back and forward from Copenhagen to Padua, back and forward. So today I will talk about the uncertainty, because since I've been working on water quality in sewer system, that's really a very uncertain topic. So my lecture is structured in these 3 blocks that you see here. I have a general introduction of uncertainty, more general, why we need to be aware of that as environmental engineering. Then I'm going through a theoretical classification on how you can classify the uncertainty in your models. And finally, I just give some example how we can survive as engineer in this very uncertain world. So we start from the buzzwords. If you are into environmental engineering now, you see a lot about attention, energy. Everybody's talking about digital twins, machine learning, artificial intelligence, big data. They will solve all our problems. They will not be, the machines will solve our problems, and there will be almost no need for engineers. The point is that behind all these buzzwords, so all artificial intelligence, big data, you name it, at the end of the day, all of them are mathematical models. And so as mathematical models, they are also uncertain. And if people forget about that, then can be dangerous. This is a picture from March last year. Last year. This is the health minister in Denmark, and he was announcing that they were closing down the country for Corona. And they were showing that graph there, where you see, well, if we don't close, we have the orange curve where our hospital will be overloaded. And if we close the country down and we stay all at home and don't go have social contacts, we keep the green line and we all survive and go through the Corona crisis happily. So, but as an engineer, what do you see? I see a deterministic model. So one simple solution. And what is actually behind, that was the calculation made behind the Corona models for all the evolution of the pandemic in Denmark were done by our colleagues from the mathematical department at the TU. And they were using basically this simple model, two differential equations with these two terms, and that's it. That's what gives you these curves. The problem is, so this is a deterministic model. You see, you run it one time, you get always the same result. But the problem is that all those parameters are super uncertain, especially last March when coronavirus just came up to the, nobody knew the rates, the diffusion rates of these processes. So there were a lot of uncertainty. So actually what was behind was this kind of model. They were running stochastic simulation, running with uncertainty behind that. So they were calculating risk and making simulations. So on the left, we have the scenario is in Danish, but on the left, we have the scenario with if we keep the social distance. On the right, we have the scenario if we still go around and kissing and hugging each other. But what you show to the big public was just the median, the black line. But what was done behind was a stochastic model that accounts for uncertainty. But you already see this is already more difficult to explain to people if you have an uncertainty behind that. It's very difficult to communicate, but it's there in the modeling. Because what is should be like tattooed in your front everywhere as an engineer, as a modeler, is this one. You have always to remember that all models are wrong, but some are useful. Models are simplification of reality. So they are inherently having uncertainty in that. You will never be able to get the exact reproduce exactly what you see in the observations. But nevertheless, they're still useful tools. So you can still use the results of the model, but you need to be aware that they are a simplification of reality. They are not the word of God. They are a tool that you have developed, that you apply to some data, and you are using to find a solution. And that's, if you think of the typical formulations of a mathematical model, is something like that. You have a model which gives you results, which is a function of time, space, input parameters, and you try to match this value, the result of the model, to the observed value. That's a nice formulation. We like it, very clean, very easy, and then we can build our model upon that, no problem. The issue is that reality is a little bit more complicated. So you have some observation that you want to model to match, but this observation have error. Your parameters have error. Your input data, they have error. Then you build a model, which is a simplification, so it is inherently has some uncertainty in it. So you have a lot of source of errors inside your model, and all of them, they will affect your results. So we switch from this nicely ideal situation where you have nice model giving you a result, where a very messy situation with a lot of terms that you don't really know what is the value, you're not really able to estimate. And this is the world you're living. The problem is how to communicate to the people that are interested in using your results. So we all agree that uncertainty is really necessary, is important as I understand from Luca, you should now have aware of the uncertainty of your model that you have been using in the course. But so as engineer, as a scientist, we all agree that it's important to do uncertainty, to estimate uncertainty, and to do the uncertainty analysis. But it's not really still a routine. And why is that? Well, here is an extract from a book about uncertainty modeling, and they're just listing some example why people don't do uncertainty analysis. And there are different things like, oh, it's difficult to communicate. It's difficult to perform. I mean, most of the times you need to run several simulations. So it's heavy computational. You need to run several simulations. It's difficult. You have so many things you decide, and yeah, subjectives. So a lot of stuff. And sometimes is also the first point is like, oh, but yeah, I have a physical model, don't really need uncertainty. I have the physics of law of gravity or things like that. I don't really need uncertainty analysis. I'm pretty sure about these equations. So a lot of factors that say, we skip it, the uncertainty analysis. We don't really need it. But if you do that, you risk to have some misunderstanding how much the model can. And an example that we usually experience almost every day is about weather models. So please, if you have a window close to by, look at what is the weather today. I look right now and I can see that in Volta Barozzo in Padova now is cloudy, nice gray sky. And this, when we look at weather forecast model, they are physically based models. So these models that are supposed to be most correct. So I checked, okay, now is gray. How was the forecast for today? And I checked different weather service. I checked an American web service, I checked so the local, the regional one, and I checked the Norwegian weather forecast, because we know in Denmark, we don't trust the Danish, so we always look at the Norwegian, which is much better. So I look at the forecast on Monday for today, and I was showing mostly cloudy, sun, and the Norwegian say cloudy. Then I check on Tuesday, and then they start saying, yeah, still cloudy, sun, and the Norwegian still stay cloudy. And they keep, also yesterday they were saying still saying cloudy, not cloudy, and so on. So for today, they didn't change a lot. If we also look the 6th, so yesterday or tomorrow, we see something like that. So for example, some forecasts switch from sunny to cloudy. Sometimes they were saying, oh, it's going to rain, and then it didn't rain, and so on. And this is something that we experience quite often. How many times you look at a forecast and they promise something, and then the day after they didn't deliver, and the people complain, oh, forecasts are always wrong. They say sun, and then I couldn't have my, then it was raining, and I couldn't have my picnic in the garden, or things like that. And you check different websites, and then you get different results, and you're complaining, oh, these models don't work. But this is, why is that? You need to understand how the model were built. And you have examples of politicians complaining like, oh, forecasts say the weekend will be raining, and then it was actually sunny and no tourists came. Was the model fault? Other example, when you're using the model for more serious example, for again, warning about big floods. This was a case from Liguria from 6 years ago, big flood, and the problem was not, the model didn't send a warning. So everybody complaining, the model is wrong. More recently, the Venice, the model predicting the tide, sometimes in 16, they were complaining, the model said it was going to be Acqua Alta, and then nothing came. So they were like, oh, the model doesn't work. And then last month, we actually the opposite way. The models say underpredicted. They say there is not going to be a big tide, and actually there was a high tide, and Mose was not open. Again, oh, bad model. The model is wrong. What is the problem? The problem is that the misunderstanding is because people don't understand how those kind of weather models are built. And sometimes there was another example from 8 years ago. You have 2 days before, you have this newspaper saying there's going to be a big flood, and then even giving you a precise map saying, okay, if you live in this area of Rome, you're going to be flooded. If you're going to be in this area of Rome, you're not going to be flooded. With such high precision, spatial 2 days in advance. That's completely crazy if you are considering how those models are built. This is completely putting too much expectations on the model, because the model cannot deliver that. Why is that? Because you need to understand how those models are built. This, for example, this is an example for the weather forecast in Denmark, how they are built. So there is the European Center of Weather Forecast that is in England, that is running a model for the northern part of the hemisphere. So they have a model that goes all the way from Northern California, Oregon to Egypt. So pretty a big model. And then the Danish weather forecast, and I guess here also in the regional, in Italy, they will be the same. They cut one piece of this model, and then they run another model with higher resolutions. And that's the small area that you see in the graph, in the chart there. But still, this smaller area is a model that goes all the way from Iceland to Ukraine. So it's a pretty big area. And all those models is divided into small pixels. And since those models has a lot of uncertainty related to the initial condition, you cannot measure the atmosphere in all the points in this big area. You cannot decide the model structure. So what they do is basically that they have 5 different model structures, so 5 different sets of equations, and then they run 5 different sets of initial conditions. So at the end, they basically run 25 models on that. So when you open the home page and you see the result, you see the results actually of combination of 25 model results. And how does the model result look like? So this is an example from a rain, and I should start the animation. So this is Denmark, and you see the forecast of a rain. So you see now rain is coming. And yes, we stop here. And what we see is those 25 model simulations. And we basically see they all agree pretty much. They are saying this is this big rain coming from the west to the east. Pretty uniform across the entire country, is something coming from the Atlantic Ocean. So the models, all those 25 models are more or less agreeing with each other. Fine, but this is a rainfall right now in winter time. This was in January, so that's pretty easy to simulate. Let's see what happens with another rain. Now we are in summer. And now we see some big rain coming in. And dun, dun, dun. We can stop here. Yes. Okay, so now we have, again, 25 different model simulations. And we can see some red in the map. The meaning is coming to be these big summer storms that are coming and flooding the city. So those big storms that are creating a lot of problems. So already here we can start see that some models didn't really show anything red. So some others say, it's not going to rain. But the majority is actually saying, yes, there's going to be a big rain. The problem is, and now I need to annotate in the graph, the problem is if you see the placement of this range. So if you look at this one, it's saying to be, that's where Copenhagen is. That model is saying there's going to be a big rain in Copenhagen, but all the others are not saying that. And for example, this one is going to be raining in Aalborg. This is going to be raining on the eastern coast. If you don't know Denmark, but basically there are 200-300 kilometers difference between those two places. So you can imagine that, yes, all the models are saying more or less there's going to be some thunderstorm. But if you're planning to have your picnic in your garden, it makes a difference if the rainfall is in your garden or is 300 kilometers away. So if you look at this graph, the results of this simulation, and you're asking model, tell me how much rain is going to be raining in my garden, and you look at this, you're basically saying this model is crap. But remember, this is a model that is predicting rainfall all the way from Iceland to Ukraine. How can you be asking the model to be precise on a single pixel of such a big model? So that's when you have this mismatch of expectation between the model objectives, how the model was built, and how you're going to use the model. So that's a problem linked to how to communicate the uncertainty. So it's important to remember that uncertainty is in any kind of models, from the super simple to the super complex model, uncertainty is there. And if you forget about that, then you are claiming, oh, the model is wrong, the model doesn't work, this is crappy result, I cannot use for anything. So again, remember, modeling is, the uncertainty is everywhere, because in a nice deterministic environment, as an engineer, what you do, you have a system and you want to optimize the system. So you cannot experiment, trial and error, and forever in the real world. So what you do, you build a model, you run a lot of simulations with a model, find a solution, and then you implement. But you have so many different factors that affect your process that you need to be aware of that, and then you have to be able to navigate around this problem. So if you push a button and run the model and blindly trust what the model is saying, then you are surely encountering some problems. You need to be aware of uncertainty and be able to navigate and use that. And be careful, because not you as engineer, but the people using your results, they will use the uncertainty for their own purpose. And uncertainty can be used as a wildcard for doing things or not doing things. A pretty good example of uncertainty used for not doing things was for climate change. For decades, one of the points of people against climate change was like, oh, the models are so uncertain, don't do anything. We don't really need to do anything. The models are too uncertain. Also, again, with the corona, there was somebody was saying like, oh no, these results are wrong, everything is in control. So in this case, uncertainty used, we don't know, we prefer not to do anything. On the other way around, uncertainty can be used to do stuff. That was a quotation from the US Minister of Defense when they decided to invade Iraq many years ago. They were saying, oh, we don't really know if they actually have a weapon of mass destruction. So just to be sure, let's invade the country. Similarly, with the COVID, country like Denmark, they were like, oh, we're not sure about what's going to happen. We go on the safe side. So they actually closed the country much earlier compared to other places in Europe. So in that case, the uncertainty used that saying, we don't know, so let's do stuff. Another example how uncertainty can be misused is about, again, from an example from Danish politics. 5 years ago, the government approved a new regulation allowing the farmers to discharge more nutrients, more fertilizers in the fields. And their point was like, yeah, they will release more and more pollution, more nitrogen, but nitrogen is already going down. That's the green line. And even if we increase this discharge, we are still below the current situation. That's the pink line. So yes, we pollute more, but it will be still less than what is now. The problem was that they forget to consider uncertainty and of those model calculation. And if you're actually doing that, that was actually a high risk that actually the pollution was actually increasing compared to the current situation. But I don't know if they did on purpose or they didn't were aware of that. That's but basically they forgot to tell about the uncertainty of this model. So they say, oh, there's going to be bad, good, don't worry, and actually turn out that they were polluting more. So that's an example how uncertainty, how people will use the uncertainty of your model for their own purpose, and then we misused it. So that's why important as engineer to be sure to communicate and find out what is the uncertainty of your model. With that, I'm gone from my first part. So I think we can take 5 minutes break and we start on this time. Okay, 5 minutes after 10. And if you have any question, please use the chat or also raise the hands. So
Thank you very much, Professor Vezzaro, for your very interesting lecture.
yes, yeah.
I'm looking forward for a continuation. I'm going to drink a coffee.
Yeah.
Quanti studenti ci sono in classe?
10. Siamo in 12 con noi due.
10, non male.
Vado
Come
a prendere...
vedi, sono molti Erasmus.
Vedo dai nomi.
Si vede dai nomi, infatti.
Bene dai, che così...
Ti riporti in Danimarca qualcuno, no?
Beh, ne ho già fregati abbastanza. Cioè.
Ne hai già fregati tanti, sì.
Sai, tipo... Non so. Beh, sì, la Valentina è passata su anche da Bisiniello.
La Valentina Poli?
No, Bisiniello. No, ha fatto, però è venuta su dopo una lezione. Yeah. E tipo l'anno scorso quest'anno ha vinto il premio per la miglior teacher all'ITU.
Ma dai.
Sì, sì. Ci difendiamo bene.
Lo so, vi difendete bene, sì, siete bravi. Va bene Luca, vado a prendere un caffè, ci sentiamo dopo.
Anch'io vado a fare il pieno di acqua. Okay, so my clock saying now we're back to 5 past. Okay, I hope you're back to the front of the screen. And now in this second part, I will go through a way to classify the uncertainty. So now I say why is important to take care of uncertainty, how people can misuse them. So now we have to go as engineer, find out where those uncertainty are, how we can classify. So if we able to bring that up to the surface, then we are also able to manage and communicate them in an easy way. So first, we need to look at what is uncertainty. And if you look at the definition from the European Environmental Agency, basically it's what we mentioned before. We have this deterministic idea of the world, this nice equation that everything is clear, neat, and anything that takes away, mess with this formulation, that's uncertainty. And what we can do with uncertainty is that we can classify in a three-dimensional perspective, and we can define the level of the uncertainty, the location of the uncertainty, and the nature of uncertainty. So these are the three dimensions: location, nature, and level. And now we go through those three dimensions, and that's the way how you can use that later to analyze the uncertainty in your own model. So we start from the location. So the location is basically where in your modeling procedure the uncertainty is. It could be at the beginning where you're defining the boundaries of the model, the framing, the equation you use, so the model structure. It can be in your data, it can be in the parameters, in the way you interpret the results. It can even be in the software or the hardware you're using. So where in the steps of the modeling procedure, where is this uncertainty? That's the location. So it could be, for example, in the context is how you define the boundaries. That's the first thing when you do a model. You define the boundaries, the time scale, the spatial scale of your model. You define one boundaries, but another modeler could, as goodly, it could define as good another boundaries. It will be perfectly fine. There's a different choice. So, well, here we have our first location of uncertainty. And this in practice, what does it mean? For example, there's an example from life cycle assessment. I have colleagues working with life cycle assessment of waste management, and they're making these calculations. And for example, in this example, you have an incineration plant where you put waste in, you burn the waste, and you generate electricity and energy. And you want to compare this solution against sending to landfill or recycling. Fine, you have one model, but what are you using the model for answer? You can look at the model to answer to, okay, what is the impact on climate change? What is the impact of human toxicity? What is the impact of freshwater toxicity? This is kind of answer that the same model can give. But if one solution that works for climate change, maybe is not so good for freshwater toxicity. So you have the same model, be careful misusing the model for answering an answer that it was not supposed to give. Another example that's linked to what I talked before is about weather forecast. We're using this model for weather forecast for they are built by meteorologists, which are looking at big scale. They're looking about one country, so they're looking at big perspective. And then people like me working in the urban areas, they take these results and they want to know exactly how much is going to rain in 1 pixel. And this is an example you see on the right. This is 1 pixel. 1 pixel of this model is 3 kilometers by 3 kilometers. So when you have a catchment of an urban area, that's a green area, you see that it's basically a couple of pixels and the entire area is covered. So I'm asking to a model that's building, simulating rainfall from Iceland to Egypt, not to Ukraine, to be precise on 2 pixels. that's really that's where I am for a source of uncertainty. So the meteorologists are happy if they are able to see is a big rain, is a small rain, and is moving in that direction. That's what they are looking at. And I want to be really precise in a 3 by 3 kilometers in 1 pixel. So if I use this forecast and I put into a rainfall runoff model to say how much water I'm going to have in that specific area of the city, basically I got these messy results, big mess, not really a good result. And I'm saying like, okay, this model is crap. But the meteorologists have a completely different glasses to see this model. This is a slide from the Danish Meteorological Institute, where they ran the model for a big rain that hit Copenhagen in 2011, €1 billion damages, big flood. And everybody was saying that, oh, nobody predicted this. Actually, they did. It was just 30 kilometers eastward. The models of the Meteorological Institute say it's going to be rain, but it's 30 kilometers east. And if you're in Copenhagen, that's basically in the sea. So nobody was worried about that. And they're like, they run the model again and they say, our model is good, look. And this is the slide they show. So what they did is they look, is our model able to predict big rain? Yes, it does. This is like 50 millimeters of rain over 6 hours. But the cell they use is 80 by 80 kilometers, because that's their perspective. They are looking, yeah, we predicted rain is 80 by 80. But if I'm in a city asking to predict the rainfall there, 80 by 80 can be anything. So that's a mismatch between the perspective, how you define the boundaries of the model. That's also a social uncertainty of how you calibrate the model. You calibrate the model to predict against one parameter, one output, and maybe you're using the model later to predict another output. Another source of uncertainty location is the structure, how you build. So you define the equations. For example, in my work, you define how many pipes of sewer pipes you want. But another model can define, oh, maybe we need more pipes, we need less pipes. They are all right. So the important thing, they're making different choices. And this is a location where you have uncertainty. So I can have a model to predict runoff in urban catchment based on simple conceptual approach. So tanks in series like that, free equation, fine. Or I can have a physically based model using this Venant equation, simulating each single meter of pipe. So I know exactly how much water I have in each pipe everywhere. At the end of the day, what they do, those models, they predict the flow at the end of the catchment. So which one is right? They are all right. But if I'm modeler one, it will choose one equation, the other modeler will choose another one. And of course, you have uncertainty in that, in the model structure. And if you're not aware of this, then you can have a problem in communications. So it's important that you are able to choose the model structure and communicate the things. Sometimes people just choose the super complex model, but this is not necessary. So you have to find a balance also between the super complex model, the simple, which equation are necessary, which are the target, what is the objective of your model. And all those choices add uncertainty in that. Sometimes you don't need a super complex model, just go for the simple. Sometimes you need super complex model because you have a complex issue to solve. But you need to reason about the process. And another thing, be careful, because people tend to use, okay, I learned this model approach at university and I don't want to learn new stuff, so I just stick to that one. So that's another problem you see sometimes in the real world, is that people just use the same model everywhere, like hammer to solve any problem. So this choice of the model structure is really essential to communicate, make sure I use this model, I choose this model structure, this to solve this problem. And that's a location of uncertainty. Another location, important location of uncertainty is data. Sometimes we are fighting to match our measurements, to match the data, and our model isn't really able to simulate this. And that's an example from the climate models. And that's the temperature series in the seawater for the last 100 years. And then there was this peak there that no model, no climate model was able to predict that peak. And they were like fighting to modify the model structure to really, for the rest of the series was really good match, but not that part. And why is that? Well, I didn't put the x-axis on purpose, because if I put, you could see that those data sets, this anomaly was between 40 and 45, 1940, 1945. And something was going around in that period in the world, something called World War II. And you could imagine that the navies around the world, they were not really busy with measuring temperature of the seawater. They were busy with shooting each other. So what happens in that period is basically that the only data available in that period come from the US Navy. That was the only one that was still keeping, collecting data. And they had a different way of collecting data in the way they were taking up the sample from the sea and measuring the temperature compared to the others. So that period of data set was actually biased. There was a bias that was not available in the other period. So in that case, the problem was not in the model, but it was in the data. So we as a models, we tend to believe like, oh, the data are, we need to match the data, the model to the data, but sometimes the problem is in the data. Another example is about the parameters. For example, if I have a model to simulate the fate of micropollutants in different environmental compartments, I use these partition coefficients. So, for example, I look for the partition coefficient, in this example, from benzene between soil and water, and I go in database where I have these values that are measured in the lab. So they are measured in the lab, they follow the procedure, so I'm pretty sure that those numbers should be pretty safe, right? But if you look at this table, you can see that even if this data well measured according to all the rules, we have a range going from 4 to 614. So we have a factor 100 in the parameters. And that's a big issue. So which number do you use? Yeah, that's a source of uncertainty. Another location is about the hardware, very small, but it's still there. Remember that we have number working with digits, 1 and 0, so a small number, one change in the memory, it can be that you have some numerical error. They are very, very seldom, but it can still happen. And another thing is that some of you maybe will build your own model, but if you go in the real life, most of the times you will use software built by somebody else. And all software, they have bugs. And actually, the more complex the model is, the more bugs you have. And if you're not aware of that, then you can have uncertainty in your results that you're not aware of that. An example, again, of this problem with you using software built from somebody else, it was the Mars Global Orbiter, very infamous example that was sent by NASA to Mars. It should be orbiting around Mars to make measurements. And there were two working groups in the NASA, one on the East Coast and one on the West Coast. They were sending the model back and forth to each other. There was a small problem that one group was working with the imperial units and the other group was working with SI units. They were not aware of that, so they were using each other's software. Results, the orbiter crashed so on Mars instead of orbiting around that. So these are the locations of uncertainty. So where the uncertainty are. Then you have the second dimension is the level of uncertainty. Here you can classify into different levels where you have the statistical uncertainty, scenario uncertainty, qualitative uncertainty, and then you go into ignorance. And now we go through that. So statistical uncertainty is where you actually are able to give a probability. So you know where the sources of uncertainty are. So you know this parameter is uncertain, and you can describe the probability. So you can propagate the uncertainty in your model and give this distribution. So you get a number. Okay, my result is 1 plus minus 2% or something like that. So you can use Monte Carlo, Bayesian methods, and so on. So you get this distribution. That's pretty easy. As engineer, we know how to handle that. Then you have the scenario uncertainty. In the scenario uncertainty, you know that you have sources of uncertainty, so you know the location, but you cannot give a probability. You don't know, oh, this parameters is uncertain, but you don't really know how much. So what you do is that you run with if-then simulation. You make scenarios. If I have a value of 10 for these parameters, then I get this result. If I have a value of 2, I get this other, but you cannot really give a probability of that. And then you can combine this statistic and scenario uncertainty. So an example is that, so you have statistical uncertainty, so you have a bounds of your result, and then you make scenarios out of that and you propagate. Okay, I have this one result plus minus something, and then if I make scenario 1, I go in the future, I get these different results. And an example of that is, again, for climate change. What they do is basically they make scenarios about the emissions of CO2. What if we continue as we do now? What if we stop from tomorrow emitting CO2? What if we stop 50%? So they make different scenarios. And then they propagate these scenarios through the climate models. And that's how you see the result from the IPCC reports. You see the statistical uncertainty, so these bounds, and then the scenario, which are the different colors. And then you can see, okay, there is no difference between the scenario, or, so for example, the orange and the red, sometimes they overlap, but you see clear difference between the red and the blue scenario. So this is the way how you present the results and you propagate that. Then you move into qualitative uncertainty, and here is more foggy, because then we are like into moving from engineering to more how people think, and there's ambiguity. Is like, okay, it's 50% uncertain probability is a lot or is not a lot. So it's really more related how people interpret the results. And an example of that is, for example, the debate that is now on the EU level about, for example, glyphosate is a pesticide, has been around for 50 years. And looking at the same data, different experts are saying we should ban it. Some others say, no, it's not a problem. And that's, the numbers are the same, but the interpretation of the expert, of the people behind that's different. So that's, we are into qualitative uncertainty. And then that's where you still know that there is an uncertainty in your model. Then you move into ignorance. And in ignorance, recognizing ignorance is that you know that something is wrong in your model, something is uncertainty, but you cannot really find the location. And then the total ignorance is that you don't really know what is wrong, what is missing in your model. So the ignorance can be that process that you're not having included and not included in the model. And that's an example of the Tacoma Bridge they built in the 40s. They built this nice suspended bridge, and they didn't really include anything, no effects of aerodynamics. That they did nice structure that was basically like a wing of a plane, but they didn't really put in their model calculations anything about that. Result, the bridge start behaving and oscillating, and at the end it collapsed. So that was something, they knew that something was there, but they didn't really put in their model, and they really, that was led to a failure. That is recognized ignorance. Total ignorance is something we are living right now. Stuff that are completely unexpected, and what they call black swan events, something that you can't even imagine that is going to happen. And we are in the middle of one of that. Nobody really saw that coming, this big pandemic. And the problem is that, as I said, those models making some, making predictions, making prediction of epidemics, none of the existing model was able to simulate this different behavior of the coronavirus. So people were making simulation, but with completely the parameters were not there. The equation was not really fit for the behavior of the coronavirus. So the model was not designed for that. And most interesting was this example about everybody's talking about the artificial intelligence. Big companies like Amazon, they're using artificial intelligence to manage their warehouse. They kind of know what we buy, so they manage their warehouse based on that. But what happens, this is data-driven models based on our behavior, but suddenly when all the world locked down, our behavior changed. We suddenly start buying yeast to make cakes at home, or those kind of things. And the model were completely not able to follow this new behavior. So the model was completely off, and they were completely going crazy with new behavior. So that was ignorance. The model were not built to predict this, behavior. So to summarize, when you're looking at the level of uncertainty, we have the statistical uncertainty where we know the location and we know the probability. The scenario where we know where the uncertainty is, but we cannot really do the probability. And then we move into the ignorance where we start knowing that it's something is wrong, but we cannot really point it out. And as an engineer, we typically stay between the statistical uncertainty and the scenario uncertainty. The other is more to the decision makers at the end. And then that's the second dimension. Then we have the third dimension, and that's the nature. And that's basically the nature of uncertainty is, can I reduce this uncertainty, yes or no? So if it's something that is linked to the process, to the natural process that you are modeling, that you're simulating, so that's the natural variability. So it's a aleatory uncertainty. You cannot avoid it. Every time you're measuring a chaotic system, so even if you make more measurements, you're still having some uncertainty, some distribution. So you cannot avoid this. Why then you have another level that is epistemic uncertainty, that if you make more measurements and then you're able to reduce the uncertainty more and more and getting closer to a good value. And that's, so you can reduce that. And then you have the ambiguity, that's kind of in the middle, that maybe sometimes you're not able to, some processes are not described in the model, sometimes you are lacking knowledge. So even if you are making more measurements, you're able to get the uncertainty smaller and smaller, but you're still missing some process, so you cannot really take out the uncertainty out of that. So that's the third dimension, the nature. Can I reduce it, yes or no? So to summarize this 3D classification, you have the location, so where in the modeling procedure you have this uncertainty. The level of uncertainty, can you quantify it? Do you know where it is? Can you quantify it? Can you give a probability or not? And then the nature, can I reduce it, yes or no? And there is a good paper that I also will give to Luca, that I will send you together with the slides. That is this one, which is very nice because then he has this scheme here, which you can follow, and you can actually take your own model or even the one that you're using now in the course, going through this classification scheme and find out where the different sources of uncertainty are affecting the results. And you can build tables like that. And so you're kind of visualizing, showing, bringing your uncertainty up to the surface. And it's really nice because then you are not hiding the uncertainty under the carpet, but you're making clearly visible and showing, look, I'm aware that my model has these limitations. And with that, I'm over my second block, and then I would say 5 minutes more break. We start at 35, and then I have the last 10, 15 minutes just to show some example of how we can, as engineers, actively use this uncertainty in our everyday life. So we start at 35.
Tesoro, posso tocarti ok?
Okay, so we can start with the last few slides, last examples on how we can, in practice, we can do that as engineer. How we can actively incorporate uncertainty in our life as engineer. So we saw why it's important, how we can bring that to the surface using this 3D classification, and how we can use it in practice now. So basically, the simple answer is safety factors. And basically, it's the approach that has been used for several years, for decades, for centuries. We know that we don't know, so when we make our calculations, we put factors in it. And you have to be careful. This is an example from the safety factors in how designing sewer pipes in Denmark. So we start, so we know that we make our calculation, we make our flow, and say, okay, in this area, we will get 1 cubic meter per second if it's raining with a return period of 10 years, and we need to make a pipe of 1 meter, fine. And then since we know that we don't know, we put a safety factor and we say it should be 20% bigger. So instead of 1.1 meter, we put 1.2 meters. So we go back before the models, before the computer stay with the hand calculations. And there was this, we know that is some uncertainty, so we just put some safety factor based on experience. The gut feeling, the good old engineer saying, oh, I think it should be 50% bigger. Blah, blah, blah. So that was the factor. Then in the 80s, people start using dynamic models. This model based on the Saint-Venant equations, very precise, you know exactly the water level in all the pipes, every meter of your pipes, everywhere in the city. So now we have the model. Now we know everything. We don't need safety factors. That was because the old guy was still doing the calculation by hand. Now we have the mathematical models. So basically, what happens is at the end of the 90s, there was basically no safety factors anymore. So engineers were making calculation with super complex model, very precise, everywhere. Then if the models say 1 meter per second, 1 cubic meter per second, you'll find, okay, we need 1 meter pipe, we build 1 meter pipe, fine. But then it starts raining more, people get flooded, and they realize that something was wrong. And they realize that, well, the input rain, well, the rain is changing, we have climate change, it's going to be raining more. Then you have these parameters, you have this coefficient of roughness of the pipes, how much is concrete, is which material you have in the pipe, and is a new pipe, is an old pipe, and then you use the same parameter in all the city. That's a source of uncertainty. And slowly, people start realizing that, oh, shit, we need uncertainty factors back. So they start putting more uncertainty factor on climate change. And actually, right now, the safety factor that using for designing is actually bigger than the safety factor that were used in the old ways when the engineer was still making the calculation by hand. So this is an example. So safety factor, that's the way of accounting for all the uncertainty in our model. You can actually calculate those by using this statistical of scenario uncertainties, and you can quantify that. But that's a practical way of incorporating the uncertainty. We know that we don't know. So when you get the results out of your model, then you get some uncertainty out of that. Another example, this is for design. The example I showed, this is for real-time control, this application. This example from the Mose that didn't close because the forecast weren't predicting high tide. That's something we experience quite often in urban drainage. And this is a simple example we have. I have a city with two areas, with two catchments, West Town and East Town, that they send the water to a treatment plant. And this treatment plant has a limited capacity, so if it's raining too much, this extra water is going directly to the river. So we have pollution of the river. And to avoid this, we built some basins. to store the extra water. So when it stops to rain, we can send the water to the plant, and we don't send to the river. So what happens in this city is that I have a rain coming from west to east. So I'm in Denmark, so it's always coming that way. So the rain right now has been over West Town and is on the way to go to East Town. So if I look how much water I have stored in the basin right now, it has been raining in West Town, so I have a lot of water there. And in East Town is just starting now, so there's a little bit water. So what I use to control these systems, I have pumps to empty these basins, and the traditional regulations of these systems is based on real-time control that says I don't know what's going to happen in the future, so to be on the safe side, I want the same volume in both basins. So I see now west is very full, east is empty. So if I want the same volume, what I do is basically I decide to pump as much water as possible from West Town, because I have to empty West Town so that then I have the same volume in both. That's what I have no clue about the future. That's the real-time control. I know only how much water I have now, but I'm smart. I have models. I have forecast models telling me how much is going to rain. So I can use what is called model predictive control. I make decision based on what the model is telling me. And if I do this, I take my model and I ask, model, tell me how much water I will have in, let's say, 2 hours. And the model say, okay, actually in 2 hours, you will have the same amount of water in both the basins. So you will have in West Town, it's not going to rain anymore. So you have maybe a little bit more water, but that's it. And then all the water the rain come in East Town. So we'll have a lot of water down there. So if we use this, and the approach is still emptying, having the same storage in both the basins, what you do when you use model predictive control, you will basically pump the same amount of water from both the basins, because in 2 hours, they will be equal. So I will pump the same amount from both of them. But that's when I use a deterministic model without uncertainty. I completely blindly trust what the model is saying. The problem was that we know rain is very uncertain. So it has been through West Town, we know that, but what's going to happen in East Town in the next 2 hours? That's really uncertainty. Is going to continue the same way, is going to turn, is going to stop, is going to increase. That's uncertainty in the input. So if I start putting this uncertainty into my model, what happens now is that, well, in West Town, it's not going to rain anymore. So I have some uncertainty, but still small. So this bounds around uncertainty is pretty small. In East Town, it's a lot of uncertainty. So the range of uncertainty is much, much bigger. So big that actually I have a risk that the basin gets full and then I'm discharging wastewater, untreated wastewater to the river. And that's this integral I see on the East Town. That's the probability that actually the basin will be full and I will have a discharge of untreated wastewater. So if I do this, I can see I have no risk in West Town and a lot of risk in East Town. So instead of looking at the volume, I can start controlling the basin, looking at the risk. And I start trying minimizing the risk instead of minimizing the volume. If I do that, well, I can say, well, I'm pretty sure about the numbers in West Town, so I can actually keep the water there. I will still that. But I don't really trust the results on East Town. So to be sure, I actually empty even more to reduce this integral, to reduce this risk. This now is this green area. So if I do that, if I start considering uncertainty, what I will do actually is pumping more from East Town than West Town, which is actually the opposite, exactly the opposite that what I was going to do if I have no clue what's going to happen in the future. So that's an example on how you can actively use the uncertainty of the model to make the decision. So instead of looking at the number that the model is giving you, you look at the uncertainty of that, and you calculate some risk. And so you're starting considering probability. So, for example, again, an example for going back to the MOSE, if they were calculating the uncertainty of those predictions, say if the uncertainty is bigger than 50%, then we raise the MOSE. So that's a way of how to incorporate the uncertainty. You will not be able to take this uncertainty out of your model, but you can still use the model calculation for that. So that's example how we as engineer can still use our wrong models to make a decision. What is very important, going back, linking to what I was saying in the beginning, is that you need to be aware that other people outside your engineering world will use those models. As a modelers, we tend to perceive the model as a center of the world, but some people will use those results. And when you do a model, you take a very complex world where you're not the only one. There will be, you are an environmental engineer, but there will be decision makers, politicians, architects, people from the environmental authorities. So you have a complex world, not only in the process, but also in the people. You simplify, you make your nice simplified version as engineers, you're nerdy, making all your calculation, get a number or some risk of that, and then send it back to the real world. And this real world will get different perspective of your results, because they will see a different way of seeing that. A very big problem is also, for example, on the wording. We are talking, all this lecture was about uncertainty. Is negative. So people like, oh, your model is uncertain, so it's wrong. Can you just make it better? And they don't realize that actually the fact that you're showing the uncertainty of your model is actually an extra point, because you're not, all the models have uncertainty. You're not hiding that under the carpet, you're bringing that. But that's things we are talking about colleagues, also we call it uncertainty is negative. Maybe you should talk about robust results. Because you're showing the uncertainty, your model results become more robust. It's very important. So it's very important when you're making your simulation, making results, remember that some people will see, oh, I will trust your model like perfect telling of the future, but it's an uncertainty. There is like a backgammon. You can make your strategies, but at the end of the day, you have the dices. You have a source of uncertainty that will mess up. So you cannot really have the perfect solution to everything. You will always have uncertainty on top of that. And with that, I'm done. So take a message. Yes, all models are wrong, but you cannot avoid it. You need to simulate, optimize environmental system. Remember, they are simplification of reality, but they're still useful tools. It's very important that you don't blindly trust your model. You acknowledge the limits and be honest about the results. Don't hide uncertainty, but actually bring it on the top, make it visible. You can classify that by using this 3D classification. That's a very nice tool. And yes, it's a very nasty way to communicate, because people will misuse it, misunderstand it, and think this is a bad thing, that you have uncertainty. So it's a challenge, and there's no really a good receipt for that. But yeah, that's the thing you will have to learn to fight and in the rest of your life outside university. And with that, I'm done. If you have any questions, doubts, otherwise the slides, I will send the slide to Luca, and my mail address is also there. If you have any questions, you want to make a project on that or things, we are open to anything. And with that is over. Now, so I don't know if Luca is still awake. He's also fall asleep.
No, I'm here. Can you hear me, Luca?
Yes.
Yes, I'm here. Grande, grazie. Thank you very much, Professor Vezzaro.
Yes, thank you very much for the lecture.
Thank you.
Good luck with the exams, and I hope Luca is nice.
I am never nice. I'm always nasty.
Good.
Okay.
It's us in
Luca,
Denmark that we are too nice. We are too good in.
grazie mille, Luca.
Di niente.
Professor, today is there the AI lesson after or not?
No, no, no.
Okay, thank you.
No. I think we have finished with the environmental impact assessment lectures. We'll meet next week for the presentations.
Okay, thank you.
Okay, if you have any questions, so we are still here for a couple of minutes when we close the classroom. Luca, è sempre molto interessante quello che insegni.
And I didn't put the example of from the Danish from the overflows. I've been fighting with the minister about uncertainty now.
Ah, sì?
Yeah, because they have this national reporting system where all the municipality, they send every year how many cubic meters of sewer overflow untreated wastewater was discharged to the environment, and how many tons of phosphorus, nitrogen, and so on. They want, since nobody's doing anything about that, they want to make some taxation like they did at treatment plant. So
Right.
if you put some tax, like the plants, they get a tax for any kilo of nitrogen, they have to pay a tax. So the minister want to put a tax also on that. But they ask, how much can we trust those numbers?
But actually, sewage overflows in Copenhagen are thrown into the sea.
Yeah. See, but it's the same. They're making the calculation for how much is discharged to the sea, because that's what they report to the also to the commission. And those models, they ask us. So there are 98 municipalities. There are 98 different ways of how they calculate those numbers. And the problem was that nobody knows. I mean, they just report the numbers, so they don't know which model they use, which parameterization, which input data. So we just say like, well, there's no uncertainty. Like, and then they have to call to the minister to report to the parliament. How is it possible that these models have no figures? Because I just brought like 150, 200% at least. And we came on the newspapers and everything, like, oh. So I became a celebrity for like one day.
Ok, Luca, senti una cosa, grazie mille, ci sentiamo nei prossimi giorni.
Yes, sì.
Se vieni a Padova, se hai bisogno di qualcosa da Padova, basta me lo chiedi.
Adesso se vuoi con Alberto che
sì.
Se lo becco.
Se hai bisogno di una dichiarazione per questi seminari te la faccio.
Ah, no.
May I ask a curiosity?
Yes.
Do you work in Denmark by your choice, or is because there are more opportunities?
Good question. So the long story is that I went there for the Erasmus. It was just supposed to be a semester. 15 years later, I'm still there. No big choice.
Okay.
I mean, it's depending on the field. It can be different. You just jump on the opportunities when you find it. So just combination of different stars, and no, it was not really the side choice. So I went there, find interesting people, interesting stuff to do. So as long as they pay my salary and there are nice things to do, it's fine. So.
Okay, thank you.
Ok, chiudiamo tutto.
Va bene. Ti mando le slides.
Ragazzi, trovate la lezione sul canale YouTube. Ok.
Buono. Buona giornata.